Gravity and Simple Harmonic Motion, Review 8. Determine the period for each physical pendulum. All objects are uniform masses. Use 9.8 meters per second squared for G. In this video, we're just giving you a little practice calculating the period of a physical pendulum. We're not going to type in the numbers here on the video. We'll show you what those are, and I'll leave it up to you to check those to make sure that they're right. But we're going to just go through this as quickly as we can. So what we have is a solid rod that has a certain mass and length pinned at one end. And when we do all these problems, we're going to need the moment of inertia, typically not about the center of mass of the object. And so we're probably going to have to use the parallel axis theorem, which is the moment of inertia around the center of mass plus this md squared term. And then we're going to put that into the numerator of this expression to find the period. Let's do the rod first. The moment of inertia of a rod about its end can be found in tables, and it is equal to 1/3 ml squared. So you could look that up. Let me put a little note here that you could find that in a table. So we don't need to use the parallel axis theorem here because the table quantity has, in a sense, taken that into account. The moment of inertia that we're going to get here is 1/3 times the mass times the length squared. And when I calculated that, I got about 9.464 kilogram meters squared. So the period for this one is going to be 2 pi times 9.464. Those units are correct. And we're going to go, the mass is 4.2. G is 9.8, we're going to say. We're going to be on Earth. And then the distance between the center of mass and the pivot point, that's what D is 1.3, isn't it? If the length of this thing is 2.6, then the distance between the center of mass, shall I draw it in there for you? There's the center of mass right there. Isn't it true that the distance between the center of mass and the pivot point is 1.3? You need to take that square root. All right. And when I calculated that to two significant figures, I got about 2.6 seconds. So perhaps you want to stop the video and check that and make sure we're okay. Let's try another one. Let's do this solid disc, and it's not pinned at the center, it's pinned at the edge, and it's kind of oscillating back and forth. We might remember in working in our last unit that the moment of inertia about the center of mass is 1/2 mr squared. 1/2 times 6.8 times the radius, which is 0.84 squared. That's about the center of mass. Will I put that up there? About the center of mass. This is for a solid disk. And for a solid disk, the equation for the moment of inertia is 1/2 mr squared. You could find that in a table. But it's not being rotated about the center of mass, so we need to add in the md squared term. And the m is 6.8. And d is the distance between the center of mass, which of course is right there, and the pivot point, which in this case is exactly r. So we're going to go 0.84 squared again. When I typed this in, I got about 7.20 kilogram meters squared. So now let's use the equation to find the period. 2 pi times the square root of 7.2, and then in the denominator, we're going to have the m, which is 6.8, g is 9.8, and then the distance between the center of mass and our pivot point here is the radius, which is 0.84. And when I calculated that out to two significant figures, I got about 2.3 seconds. That's how long it's going to take to oscillate back and forth. So these are plug and chug problems, which we haven't done a lot of in these videos, but let's do a couple more. And again, feel free to stop the video if you want to do these on your own ahead of time, and then you can check and make sure that you and I agree. Let's try this one. here we have a solid rod, but it's rotating not about the center of mass, which is right about there, but it is oscillating about that point right there. We need to find its moment of inertia. And to do that, for a solid rod about its center, the moment of inertia, you can look this up in a table, is 1/12 ml squared. The moment of inertia about this point is going to be 1/12. The m is 0.88. The length is 1.8. We need to square that. Plus, we're using the parallel axis theorem here. We need to multiply the mass times the distance between the center of mass and the pivot point. Now, the length of the rod is given as 1.8. So the center of mass is 0.9 meters from the end, and the pivot point is 0.7 meters from the end. So D, which is that distance right there, is going to be 0.2 meters. So that's what needs to go right here, 0.2 meters, and we need to square that. All right, when I calculated that number, I got 0.2728, pretty small, 0.2728. The unit for moment of inertia is kilogram meter squared. And now let's use the equation for period. Period is 2 pi times the quantity here. We got to take the square root. 0.2728 is in the numerator, and then in the denominator we have the mass, which is 0.88. G is 9.8, and then as we determined, the distance between the center of mass and the rotation point is 0.2. So we've got to type that in. And when I type that in, I got 2.5 seconds. All right, let's try one more. Now we have a thin ring pinned at its edge. And a thin ring from the table, about its center of mass, a thin ring has the moment of inertia mr squared. The moment of inertia for this one is going to be mr squared, right? You do the about the center of mass first, and then you have to do the md squared portion. So plus m. Now, what's d? Well, the center of mass is right there. D and r are the same. So in essence, you end up doing the same thing twice. Mr squared, that's I about the center of mass. And then this portion here is the md squared bit. And when you do that, you end up with about 10.368 kilogram meters squared. All right, we're nearly done. Let's type in the period. And I got 3.1 seconds.